Hi, I'm Dan Hendrycks, a PhD student at UC Berkeley. In this presentation, I should like to discuss how to perform anomaly detection for large-scale image classifiers and large-scale natural language processing models. I'll focus on data that is naturally occurring, and I won't focus on data that appears in very closed contexts. So with that out of the way, let's get into some practical techniques for detecting anomalies in real-world scenarios. A natural question is, how do we detect anomalies in the first place? Well, anomalies or out-of-distribution examples are fairly difficult to detect, and there are a lot of techniques lying around that many people think might be effective for their detection, but usually aren't that efficacious. For instance, one class, support vector machines, if you fit one of those models to the raw images through scikit-learn, well, the resulting detector won't be very good. Even if you do one class SVMs on top of deep neural network representations, you'll tend to do better by using some simpler technique. Kernel density estimation is another natural solution where let us get a density estimation model over the raw image space. But unfortunately, these techniques don't work that well when your input size is particularly large. They tend to work better when the dimensionality of your data is much smaller or when you have highly structured data. You could think that maybe we shouldn't be looking at the raw pixel space. Maybe we should be getting some type of embedding, like say with SIF vectors, and then do a mixture model on top of that. You might get some mileage out of that, but it's easier to use neural networks. But that isn't to say use all neural networks. For instance, autoencoders are not that effective for complex data. Might be useful for MNIST and simple digit classification, might be useful for some type of medical data, but generally won't be useful for images of the complexity of little thumbnail images from, say, Flickr or something like that. Even images that small, but still about the natural world, will not be well served to be approached with autoencoders. And there's another technique that has a fair amount of popularity in the research community, but isn't that practically effective, which is using dropout uncertainty. Generally, it can sometimes provide a little boost, but often increases the computational expense substantially. So with that out of the way, what's a way to detect anomalies more simply? Fortunately, deep networks make it so that you don't need a lot of those older school type of techniques like, say, one-class support vector machines. What you can do is you can train a classifier and repurpose that as an anomaly detector. So for instance, if I have a CFAR10 classifier, that is, say, a classifier that classifies an image as, say, a dog, a cat, a deer, or so on, if I look at its prediction probability, that can serve as a good anomaly detector. So let's look at how that's computed. There's the vector L, which are the logits, which is the neural network's vector produced for an image before it's fed into the softmax. And then those logits are fed into the softmax, and then you get a probability distribution over the different classes. So then you can perform anomaly detection by looking at the maximum confidence from that probability distribution. So basically, look at the classifier's confidence, and that is often an effective out-of-distribution or anomaly detector. So consequently, typical images will tend to have high confidence, and less usual images will have lower confidence. Their confidence still might be high, but they're still usually sufficiently lower than that of in-distribution or typical images. So that's one way you can detect anomalies. Just look at the confidence. Here's a concrete example on a small-scale image. This image is from CFAR10, so it's 32 by 30 pixels. It's kind of blurry, but it's a dog, and the dog class has high probability mass. There's a bit on the cat class, as you can see, though. Generally, these sort of images will have high confidence and won't be thought anomalous. Meanwhile, if the image was something irrelevant that didn't belong to any of these classes on the bottom, like, say, a banana, then the confidence of the classifier would generally be much less. So that's one way we can detect anomalies out of the box. I should note that for these small scale image data sets, the classes are very nicely carved up and disjoint. But when we move to large scale images, that often isn't the case, which makes this baseline not as. So we just looked at small scale image classifiers. Let's look at an ImageNet classifier, which is a large scale image classifier. It takes in higher resolution images, so the dog is of higher resolution. But since ImageNet has got 1,000 classes in this case, we have a bit of uncertainty as to the image's actual classification. Is it a Norfolk Terrier? Is it an Irish Terrier? Is it a Norwich Terrier? I personally don't know. And the classifier doesn't have as much confidence. It's just the confidence is distributed among some reasonable alternatives. So in this situation, looking at the maximum confidence isn't as good of an idea. A way around this case where if you have large-scale images and you've got a lot of similar classes, you might not want to use the maximum softmax probability. What tends to work better empirically is using the maximum logit instead. So rather than taking the maximum of the probabilities, you take the maximum of the second to last or penultimate layer of the deep neural network. And then you use that for anomaly detection. So consequently then, in distribution images or non-anomalous images will have a higher maximum logit than that of out of distribution images. Out of distribution images will have a lower maximum. And so then, depending on your application, you can set a threshold to separate between those two fairly reliably. But of course, it's not perfect. Even so, doing the maximum logit when you've got a lot of similar classes tends to work better than using the maximum softmax probability. And they're just about as easy to implement as each other. So better performance, same difficulty in implementation. So a relatively. We've just seen a simple technique for detecting anomalous large-scale images. Let's turn to another application context, that of anomaly segmentation. In this context, we have an image that we want to segment, but the scene may contain some anomalous artifacts. In this situation, we have a scene that may be seen by a self-driving car of some sort, but the scene is anomalous because it has a sheep. We should like to segment the sheep, and maybe if we can detect the anomalies, the car should trigger conservative fallback policy, like steer away from it or pull over, something like that. So one way to perform anomaly segmentation is also by using the maximum logit. Here's how the maximum logit looks compared to some other techniques. In this situation, the input is a scene on a road where there's a helicopter in the middle of the road. In the second row, there's the ground truth, and then there's the model's prediction. But if we try to estimate its uncertainty and have it tell us where the anomaly is, well, then we see that the maximum logit seems to give the best overall heat map of where the anomaly actually is. It does better than the maximum softmax probability, and compared to some other techniques, let's just say autoencoders or Monte Carlo dropout, the maximum logit does best. So as it happens, the maximum logit is useful for large-scale image classification and also for anomaly segmentation for large-scale images that have very diverse backgrounds and lots of different objects. So for fairly complex scenes, this also seems to be the best plug-and-play baseline. I would like to note that I'm not saying that the maximum logit or any of these techniques solve the problem. Certainly not. In a recent paper, I and my collaborators showed that many of these models still make fairly ridiculous decisions. So if you take an ImageNet model and you show it some classes that it had never seen before, it makes the wrong prediction with very high confidence on some types of inputs. So for example, an ImageNet classifier with a certain restriction over its classes has never seen garlic bread before, but it has seen a hot dog. So when it sees some bread, it thinks that the garlic bread is in fact a hot dog incorrectly. So although we have some traction on the on detection of large-scale images, they're still not highly reliable, unfortunately. So future research is required. I'd just like to throw that caveat. Finally, let's turn to anomaly detection or out-of-distribution detection for natural text. In a recent paper, we showed that if you use transformers such as, say, BERT or Roberta T5, those sort of models, they tend to do much better at anomaly detection than a lot of the previous models like, say, LSTMs or a bag of words or averages of word vectors. So this plot has a lot of data sets in it, so consequently some of the labels like 20 news groups, don't worry about those. Basically, what we did was we took a BERT-based model, fine-tuned it to do sentiment classification of movie reviews with the data set called SST, the Stanford Sentiment Tree Bank. And what we did was we showed it examples from other distributions. 20NG would be 20 news groups, so we showed it news articles. And clearly that is anomalous, given that the model was trained to classify the sentiment of movie reviews. And if we took the maximum softmax probability, it was able to reliably or more reliably separate out anomalies than some of the previous architectures used in natural language processing. I'll note that I'm using the maximum softmax probability because the classes are quite dissimilar. So there are a few classes. In those situations, it still makes plenty of sense to use the maximum softmax probability. So the maximum logit isn't necessary. Maximum logit will perform approximately the same in that situation. If we look at it on average, the false alarm rate is generally much lower than with BERT-based or transformer-based models compared to many of the previous architectures. So I would suggest looking at transformer models if you are working with natural language text and use their prediction confidence for uncertainty estimation, whereas previously the uncertainty estimates of deep learning models for natural language text weren't that good. So, in summary, I should like to suggest using the maximum logit when you've got large-scale images that have that fall into one of many classes, like say one of 1,000 classes or more. Or if you're needing to perform anomaly segmentation over natural images, then the maximum logit is a fairly straightforward baseline to use. If you're not having to classify one of, say, 1,000 classes with your image, then maybe the maximum softmax probability will be suitable for you. I should note that throughout this presentation, I didn't talk about some more cutting-edge techniques, such as, say, outlier exposure, because those require more implementation and are still somewhat newer in the research field. I should also like to suggest using BERT-based models or transformer-based models if you're doing tasks with natural language. Previous models in natural language processing, in my experience, have had very unreliable uncertainty estimates and weren't very good at detecting anomalies. But BERT-like models are comparatively quite good. So if you're needing an out-of-the-box solution for natural language processing, might just use a BERT-based model and look at its prediction confidence, and that will tend to give you a lot of mileage. So thank you for your time.